In a conventional design process, engineers are posed problems. They keep iterating until hopefully they get a solution. What we're trying to do is leverage the transformational power of machine learning to enable this productivity enhancement. In the inverse design process, what we try and do is we try and develop a tool, effectively some function representation, that is capable of representing the ultimate designs as functions of the problem definition. The Iowa State team is developing an inverse design capability for organic photovoltaic devices. This tool will ideally tell them what is the right morphology for these individual organic photovoltaic cells that optimizes the performance of these devices.
Conventional strategy is to take a certain configuration, painfully solve the full partial differential equation, and get out the answer. So our product is essentially going to significantly reduce the time it takes to solve by doing some machine learning neural network offline. And so this scientific machine learning tool will essentially allow the end user, in this case the designer, to essentially very rapidly explore different what-if scenarios of what if I change my configuration to this one, what if I change my configuration to something else, and explore what-if scenarios, estimate robustness of these, figure out sensitivities of these parameters in near real time.
Our specific contribution is to design what are called deep generative models, a particular form of machine learning models, which are able to explicitly utilize known physics equations or physical laws in the design process. Right? So we don't do this in the lab, we do it in silico. Right? So that accelerates from several years to say several weeks or days. So the hope is by developing our machine learning models, we are further reducing the time from days and weeks to minutes and seconds. So we can very quickly produce new designs which satisfy certain properties and to present it to the practitioner, and they can make a decision as to whether to manufacture this or not. So RocketML has been helping us in building the infrastructure, so the computational infrastructure to scale up our simulations and our ability to make accurate physical predictions to much higher resolutions.
So you need to basically take the prototype problem and make it production grade. And where we come in is we basically work with ISU researchers and understand the computational aspects of it and computational bottlenecks of solving the problem at scale. And we provide a software that bridges the gap between prototype and production.
Anything that is in the science and engineering space, the cost of discovering the solution significantly can be reduced, and as a result, the end users will see lower cost and better solutions.
I've really been amazed at the progress they've been able to make. I mean, certainly these techniques, I'd say they've demonstrated to be effective at solving the problems that they're trying to solve. And also the techniques that have been developed in many cases are very transferable to other problems.
We think this may be a paradigm shift of the idea of scientific machine learning can allow near real-time analysis of complicated engineered systems, will revolutionize how we perform design and optimization of the next generation of engineered systems.